Hello friends, in this discussion we are going to look at double integrals. Now we must understand that integration is one way of finding area under a curve, between a function, for example, f of x, a function such as f of x equal to x squared between this curve and the x-axis, for example. And to determine that area, we say integrating between limits, for example, 1 to 2 of x squared with respect to x. This gives us the area between this curve and the x-axis in the limits 1 to 2. So now, this single integral, or just one integral, gives us a two-dimensional area. Where we have two integrals, we get a three-dimensional volume. Integrals of such can be, for example, if we integrate from A to B, and we integrate again from C to D of a function xy, okay, dx, dy. And this is meaning that you are going to have this function of x and y that you're going to integrate between uh, where, for example, here, this is the first, what is inside here is integrating this function with respect to the x-axis. So the area in between the x-axis and this function x, y, and at limits c to d is what you are dealing with here. So if I multiply by the distance, in the y direction from limits a to b, we will get a two-dimensional volume. That's what we are talking about here. And three integrals, of course, will give you a four-dimensional hypervolume. The four integrals give you the five-dimensional hypervolume, etc., etc. So let's dive into this and see how we can deal with double integrals. So let's take an example. We are integrating from 0 to 2, 1 to 3 of a function x y squared with respect to y. Let's begin with respect to y dx. And this is obviously telling you that we are integrating this in the region of the values of x here. We are talking about 0 to 2, and the values of y, 1 to 3. That's what we're talking about. So if I, for example, could draw on the three-dimension space, if this is z, this is x, and this is y, then I'm talking about along the y I have 1 to 3, maybe let me call this 3. Then on the x-axis, I'm talking about 0 and 2. So I'm meaning this region, okay? This region, this exact region. This exact region. So if I move it up, okay, if I move it up by integration, I will be, because up we are talking about the f of x, this is f of x, y. It's what is going to give us z. So if we integrate that, this rectangular region, then as we go up, we'll get a volume. So let's move ahead and deal with this problem. So whenever we meet such a scenario, we are dealing with this first, because what is inside here, we shall integrate it with respect to y, and later on, whatever we get, it will remain with x in it, and then we integrate that function of x with respect to x. Now, let's move and we see. So let's work with what is inside first. So inside we have integrating from 1 to 3 of xy squared with respect to y. So meaning if we are integrating with respect to y, this is going to mean that x remains a constant and y is what is changing. So what does this mean? I'll have x y cubed divided by 3, okay? And if I evaluate it on limits 1 to 3, this is what I will get. I'll have, first of all, x out of 3 into, what is this? This is going to be 3 cubed minus 1 cubed. And what is this going to give us? This is going to give us 27 minus 1 is going to give us 26x out of 3. So what does that call us to say? Is that now we are going to be remaining with integrating from 0 to 2 of 26x out of 3 with respect to x. So if I integrate this, I'll have uh, 26x squared divided by 6. I evaluate this from 0 to 2, and this obviously gives us 26 out of 6 into, I will have 2 squared minus 0 squared. So this is going to be 4, 4, and 4 I divide it by 6, so I'll have 26 times 2 divided by 3, and this gives us 52 out of 3. So integrating from 0 to 2, 1 to 3 of xy squared with respect to y, x will give us 52 out of 3. So that is it. Let's go ahead and look at another example.